Good morning, Townview. Welcome back to Chemistry Online.
Let's go ahead and get started. So today we're going to be talking about periodic trends. Last time you were in here, we talked about all these trends. Can anyone tell me what radius is when we're talking about atoms? What is radius? All right, so basically when I say radius, what am I talking about? Okay, so if I tell you one has a radius of 1, an atom has a radius of 1, and another one has a radius of 2, what am I telling you about these atoms? All right, so I'm telling you relative size. I'm telling you one is larger than the other one. So first thing we're going to do is we're going to define atomic radius. So atomic radius, it's really hard to measure the atomic radius by going from one side of the from the electron cloud to the other side of the electron cloud. So what we actually do is we measure from the center of one nucleus to the other nucleus, and then we cut that distance in half. This is a definition that you guys need to know. So atomic radius is half the distance between the nuclei of two identical atoms that are bonded together. Right here it says that it's a measure from nucleus to nucleus divided by 2. You don't need to write this. It's just reiterating what it says in the definition. And I'd like for you guys to know the actual definition. This next part you absolutely don't want to write. So a larger atomic radius means a larger atom. That one should just be intuitive. Okay, so atomic radius, it increases as you travel down and to the left on the periodic table. So you don't need to write this statement. What I'd like for you to do is draw a little periodic table. Yours can look better than mine. But basically a rectangle is perfectly fine. There's your periodic table right there. And then you're going to draw an arrow going from right to left. That's telling you that atoms are getting larger as you go from right to left. And then from top to bottom means atoms are getting larger as you move downward on the periodic table. If you want to put an arrow going in this direction, that's fine too. But I need to know that you guys know right to left is getting larger, and then top to bottom is getting larger. So this part we discussed last class. Let's see what y'all remember. I don't want you turning back in your notes. Let's see if you remember any of it. So why do elements get smaller across a period? So why do elements get smaller as we go from left to right? What's happening that's causing the atoms to get smaller? All right, so you're increasing the number of electrons, you're increasing the number of protons, you're increasing the number of neutrons. Why are atoms getting smaller as you go from left to right? All right, so what I'm hearing is Coulombic attraction, which is correct. It's the charge between the positive and the negative. So as we move from left to right, we're increasing number of protons, we're increasing number of electrons. And when that happens, what we're doing is we're increasing the nuclear charge. What is the nuclear charge? It's the charge coming from where? The nucleus. And what is that, a positive charge or a negative charge? It's a positive charge. So as we increase the positive charge, there's a stronger pull on the electrons, causing the atom to get smaller. This is the question you're going to see on the test. You're going to be asked the why. It's not just which element is larger. It'll say something along the lines of this. Lithium is larger than carbon. Why is it that carbon is smaller than lithium, even though it's got more protons and electrons? So you'll be answering why questions. That's what you need to be prepared for. Yeah. I haven't decided yet. I'll let y'all know. You'll know in advance. All right. Any questions on nuclear charge? All right, let's move on. So why do elements get larger as we move down a group? So why are they getting larger as we move down a group? What was that?
Because the distance and the distance between the nucleus and the outermost shell is increasing.
That's true, but why are the atoms getting larger as we move down a group? So here's group 1. Why is lithium larger than hydrogen? What does lithium have that hydrogen doesn't? All right, more shells is correct. So how many shells in period 1? 1 shell. How many shells in period 2? How many in period 3? And then period 4? So every time we go down a period on the periodic table, every time we go down the group, we're adding an additional shell, which is the electrons. So we're adding electrons. That's what makes these atoms larger. And we're adding shells, and the shells are why they're getting larger. So additional electron shells or electron cloud. So here we have effective nuclear charge. So what is nuclear charge? We already discussed this. The nuclear charge is going to be the charge that comes from the nucleus, which is the positive charge caused by the protons. But effective nuclear charge, that's got its own definition. So the formula for that is ZeFF. You don't need to know this formula. I don't want you to write this. I just want you to know what effective nuclear charge is in case you come across this type of question, which you will on the assignment you're going to work on in a minute. So effective nuclear charge, what it's basically asking you is this electron, how much of a pull does it feel from the protons? So does it feel the full force of the protons, yes or no? No. Why not? Because it's not right next to it. So what's blocking off the positive charge? All right, good. Oh, not the valence electrons, but the other electrons. So this electron, it doesn't feel the full force of the nucleus because of these 2 shells. So here's how we calculate effective nuclear charge. So this right here is magnesium, and magnesium is number 12 on my periodic table. It's right here. And magnesium has 12 electrons. So we put our 12 electrons there, and then we subtract the number of electrons that are between our valence electron and the nucleus. So on this shell, in the first shell, how many electrons do we have? 2. And then on the next shell, how many do we have? 8. So 2 plus 8, that's going to be 10 electrons are blocking this valence electron from the nucleus. So we're going to subtract 10. That gives us an effective nuclear charge of 2. Okay? So that was magnesium. That's for magnesium. If we were to do lithium, lithium is right here. What's the effective nuclear charge of lithium? It's going to be 3. That's our number of electrons. How many electrons are shielding lithium? 2. Just the one from helium and the one from hydrogen. So what's the effective nuclear charge? 1. It's going to be 1. What if we did chlorine? So chlorine has how many electrons?
17.
It's got 17. How many shielding electrons? 10. Good. So it's these 8 right here plus these 2, which is 10. So what's the effective nuclear charge on chlorine? It's going to be 7. So group 1, what's the effective nuclear charge on group 1? 1. What's the effective nuclear charge on group 2? Group 13? 3. Good. 14? 15? 16? 17? 18? There you go. So that's effective nuclear charge. And that's how you calculate it. That's how we get to those numbers. Any questions on this?
So there was an issue with the audio on my last recording, so I have to re-record this section. So let's go ahead and go over the atomic radii trends. All right, so it says circle the atom with the largest atomic radii. So let's line these up. So here's this one. If we look at it on the periodic table, it's right there. And what we know about everything in this row is they have 5 shells. Everything in this row has 2 shells. Everything in this row has 3 shells. So if we're looking for the thing that's going to be the largest, it's going to be the one with the most shells. So that's going to be this one in our examples. Next set is going to be this one right here, this one right here, and then this one right here. And we know that atoms get smaller as we move this way. So the farther they are, the closer they are to this, the larger they're going to be. So in this example, it's that one. And then in our last example, we have this one right here, this one right here, and then what's the last one? It's right here. All right, so these two, they have the same shells. However, this one's got a larger nuclear charge. This is going to be the smallest of the three, so largest is going to be this one. Next one wants us to put these elements in order by increasing atomic radii. So increasing means smallest to largest. So we're increasing smallest to largest. So let's go ahead and figure these out. So let's compare the first two. So we got sodium phosphorus. That's going to be this one. And then this one. So they're in the same period, which means we just need to look at nuclear charge with this one. So this one is going to be smaller, and this one's going to be larger. And then let's find the last one. So here's our last one, and it seems to be larger than sodium. So that one's going to go here. And that's it. That's our arrangement. And then last question, which of these elements has the largest atomic radii? It's going to be this one right here. So everything in that corner is going to be larger than the things in the other corner. Here we're going to have the smallest things. So that's it right there. Let's go ahead and move on. All right, so ionic radii. Here's what you need to write. You need to know what an ion is, and that's just going to be a charged particle. And then there are two types of ions. We'll discuss those on the next slide. Over here, there's just another term you want to know. So parent atom, that's going to be the original atom. So over here we got sodium, and then here we have sodium plus. So the parent is going to be sodium, and the daughter ion is called, that's going to be the sodium plus. Ionic radius, that's just going to be the radius of an ion. And what you want to know is, so let's write our definitions for ions first. So cation, that's going to be our positively charged ion, and it becomes positively charged by losing an electron. Over here we have our anion, and anion just stands for A negative ion. That's the best way to remember it. And they become negatively charged by gaining electrons. Now when we talk about their size, what you want to know is over here we're removing an electron. So with cations, an electron is being taken away. So think of it like this. We have lithium, and lithium has the first shell with 2 electrons, and then it's got the second shell with 1 electron. If it were to lose this electron right here, what's going to end up happening is it's going to become smaller because it just lost an entire shell. So same as what's going on with sodium right here. So it's losing an electron, which makes it smaller. So cations, they're smaller than their parent atoms. That's what you want to know. So cations are smaller than their parent atoms. Anions, these are gaining electrons. They're gaining electrons without gaining protons, so we're not increasing the nuclear charge. However, as we increase our number of electrons, our atom becomes larger. So chlorine minus is going to be larger than chlorine. So that's it. That's what you want to know about ions. Let's go ahead and move to the next one. So over here we have our examples. So ionic radii, circle the larger ion. So here we have a parent chlorine, and here we have a anion. So this one gained an electron, so this one is going to be larger. Over here, sodium lost an electron, so the original is going to be larger than the ion. With nitrogen, this one gained 3 electrons, which means it's larger. Here with iron, iron lost 2, and then over here it lost 3. So this one's going to be the larger of the two. And then here we have C plus 4 and then C minus 4. Minus 4 gained the electron, so it's going to be the larger of the two. Let's keep going. Don't worry about any of this. So next up we have the octet rule. And what is the octet rule? It tells us that atoms tend to prefer to have 8 electrons in their valence shell. There are exceptions to this. Let's discuss the exceptions. So I brought in a periodic table, that way we can actually discuss these trends as we, not the trend, but the octet rule. So what is the octet rule? It tells us that all atoms, they want to have 8 valence electrons. And what we know about valence electrons is this group has 1, this one has 2, this one has 3, 4, 5, 6, 7, and 8. So everything wants to be like a noble gas. They have different ways of doing that though. So for something like fluorine, what it's going to do to be like a noble gas is it's going to gain a single electron. When it gains that electron, it's going to have a charge of -1. Oxygen, it's going to gain 2 electrons, so it's going to have a charge of -2. Nitrogen, it's going to gain 3, it'll have a charge of -3. Carbon is going to be plus or -4. We'll discuss why in a minute. And then boron is going to be +3, which means it'll lose 3 electrons to become like helium. So this one goes in the opposite direction. Beryllium is going to lose 2, so it's going to have a charge of +2. Lithium is going to lose 1, so it's going to have a charge of +1. And these charges, they apply to every single thing in that group. Now, so what is the octet rule? It's telling us everything wants to be like a noble gas. Another exception to this is the fact that helium only has 2 electrons in its octet. So helium doesn't really follow the octet rule, and neither do these elements right here. So boron, beryllium, and lithium. Rather than wanting 8, all of them want 2. So boron gets the 2 by losing 3, beryllium loses 2, and then lithium loses 1. So those are the exceptions to the octet rule. Everything else is going to follow the octet rule and wants to be like a noble gas. So bromine is going to gain 1 electron. Selenium is going to gain 1 electron. Phosphorus is going to gain 3 electrons. Potassium is going to lose 1. Calcium is going to lose 2. So everything else will follow the octet rule to have 8 valence electrons. And the reason they do this is because all atoms, they want stability, and they become more stable by losing electrons. Noble gases, they have an octet, which means these are the ones that don't really care about the octet rule. They already have their 8, so they're not trying to gain stability in any way. They don't need to lose or gain electrons. So let's keep going. All right, so our next trend is going to be ionization energy. So let's go ahead and write down the definition. Ionization energy is the energy required to remove an electron from an atom. And nonmetals, they're the ones that have the higher ionization energy. So the reason for that goes back to the octet rule. So everything on the nonmetal side, you can see all of these things over on this side, they're going to gain electrons. They don't want to lose electrons, they want to gain electrons. Whereas all the metals, so everything on this side, they're willing to give up electrons. So these are going to have the lower ionization energy on this side, and this side will have the higher ionization energy. So nonmetals, they have a higher ionization energy. And if we look closely here, what you're going to find is that the noble gases, they actually have the highest ionization energy. I can't zoom in and right. Let me see if I can laser. Nope, can't zoom in and laser at the same time. All right, so let's just zoom in. So you can see that helium is the thing with the highest ionization energy, and there's 2 reasons for that. One reason is because it's so small, it's really difficult to take an electron from it because of the really high nuclear charge, because the protons and the electrons are so close to each other. And you can see that the ionization energy is going to decrease as you move down the noble gases. So neon is lower than helium, argon is lower than neon, krypton is lower than argon. So that trend moves as we go down the periodic table. The ones with the lowest ionization energy are going to be the group 1 elements. So you can see that lithium is very low, which means it's very willing to give up its electron. Sodium is also very low. Potassium is lower than both of them. Rubidium is lower. Cesium is lower. And then francium is going to be the lowest. So the reason francium has such a low ionization energy is francium is so large, the electron is really far from the nucleus, so it's got a very weak nuclear charge. And because it's got a weak nuclear charge, it's really easy to take that electron away. Anytime you're taking an electron from an atom, energy is required. With francium, very little energy is required. And this is why group 1 elements are so reactive. So all of these elements that you're seeing down here, the ones with the lowest ionization energy, these are all the most reactive metals on the periodic table. So going back to over here. All right, so the lower the ionization energy, of an atom, the easier it is to remove an electron. So high ionization energy is hard to remove that electron. Low ionization energy, it's easy to take that electron. So here's the way that trend moves. So francium is the lowest ionization, which means very little energy is required to take that electron. Highest ionization energy is going to be helium, which is a noble gas. so helium. And this trend works, so ionization increases as you move to the right. So the noble gas in each group has the highest ionization energy. So krypton is higher than boron, argon is higher than chlorine. So this trend includes the noble gases. And this is the way you want to learn it. So their ionization energy increases as you move up the periodic table and also increases as you move to the right. If you want to write this statement, you can, but what I would do is I would make sure to draw a little periodic table, something like that, and then put in your arrows. So ionization increases as you move up and then to the right. Now, another thing I wanted to include, so very often you'll see that it's labeled as first ionization energy. The reason for that is there are multiple electrons. So let's say something like magnesium. No, let's say something like beryllium. So beryllium has 2 electrons in the first shell, and then it's got 2 electrons in the second shell. So this electron requires a certain amount of energy. Let's say that it requires 900. The second electron is not going to require 900. It's going to be different. So this one could be 800, or it could be 700. So first ionization, they're just talking about the first electron that you're removing from an atom. And that number does change. So if you come across first ionization, don't be confused by it. It's the same as ionization energy. You're never going to be asked for second ionization. It's always going to be first, which is the same as what we're talking about here. All right, circle the atom with the highest ionization energy. That means the one that's closest to fluorine. I see fluorine on here twice, so I'm going to remove fluorine. I'm going to put in silicone. So fluorine, oxygen, boron, highest ionization, that's going to be fluorine. Arsenic, nitrogen, and phosphorus. So these are all in the same group. They're arranged like this, so it's N, P, A, S. So nitrogen is the smallest, which means it's the most difficult to take an electron from it. Last one we have is silicon, carbon, and lithium. So silicon, carbon, and lithium. So the most difficult one to take an electron from will be carbon. So silicon is, the way they're arranged is carbon is here, silicon is here, and then lithium is over here. So highest ionization will be carbon. Because it's smaller than silicon, it's going to be more difficult to take an electron from it. All right, so our last trend is going to be electronegativity, and this is going to be the ability of an atom to take an electron from something else. We often refer to this as stealing. So it's when one element steals an electron from another one. So the higher the electronegativity, the easier it is for that atom to take electrons from something else. One thing I want y'all to notice about this is the noble gases are excluded from this trend because they have no interest in stealing electrons from something else. So the higher the electronegativity, the greater the attraction for electrons, and electronegativity increases as you travel up a group and to the right on the periodic table. So electronegativity increases as you move up and to the right. So the reason it increases as we move up is because the element is smaller and it's got that higher coulombic attraction. And the reason electronegativity increases to the right, again, is because it's smaller. So the smaller the element, and over on this side, this element just wants one valence, it just wants one more electron, whereas this one wants 2, this one wants 3, this one is plus or minus 4. So because fluorine only wants 1 electron, and it's so small, it's going to have the highest ionization energy. Highest electronegativity. It's really good at stealing electrons. Now, how is this different from ionization? So ionization is, so fluorine, let me draw a fluorine for y'all. So here's a fluorine, it's got the 2 valence electrons here, and then it's got the 7 here. So fluorine, it wants 1 more valence electron. So it's really holding onto its electrons very tight. Also, because it's small, because of that really strong coulombic attraction, it's really hard to take an electron from it. So its ionization energy is really high. So ionization energy is really high. Electronegativity, because it only wants 1 more valence electron, it's got a very strong attraction to other elements, to other electrons. So its positive charge, also because it's so small, its coulombic attraction is really high. So its nuclear charge is really high, which is why fluorine is so good at stealing electrons. Nothing is better than fluorine at stealing electrons. So over here it says circle the atom with the highest electronegativity. Anytime you see fluorine, that's the answer. Next one is going to be lithium, nitrogen, oxygen. The way these are set up is lithium, nitrogen, and oxygen. And these are all in the same period. So we're just going to look at the one closest to fluorine, which is going to be oxygen. Last one is going to be silicon, germanium, and arsenic. And the way these are set up is Si, Ge, and As. So this one's actually a tough one. Let me pause right here. So you're not going to see a question like this one because so arsenic just wants 3 electrons. Silicon wants 4, but silicon is also smaller. So this one's more of one of these tougher questions. Correct answer for this one is going to be silicon. Not by much, just by a little bit. So this one's electronegativity, and you're never going to need to know this, is 1.8, while arsenic is 2.0. Again, you're not going to see a question like this, but yeah, those are the reasons. All right, and then here our last slide is just going to be all of the trends side by side. So let's take a look at these. So atomic radii, it increases as we move to the left. And the reason for that is a decreased nuclear charge, and it increases as we move down because we're adding shells every single time we move down a period. Ionization, it increases as we go up because atoms are getting smaller, and then it increases as we move to the right because of the increased nuclear charge. So electrons are more difficult to steal when they're held so closely by the nucleus. And then lastly, we have electronegativity. Again, noble gases are completely excluded from this trend. They have no electronegativity. And the lowest electronegativity, we're going to exclude noble gases, is going to be francium. So francium is going to be the lowest, and the highest will be fluorine. And you can see that those are the ones that you want to remember. With atomic radii, francium is the largest, fluorine is the smallest, if we exclude the noble gases. If we include the noble gases, helium would be the smallest. After helium, it's going to be hydrogen. And then after hydrogen, then it would be fluorine. Actually, then it would be neon, and then it would be fluorine. So neon, and then fluorine. So just go ahead, write what you need from this, and good luck on your test.
If you don't know how to do chemistry, hit that subscribe button. Let's go!